This is the first of what is hopefully going to be a reasonably short series of lectures on the subject of thermodynamics. Note that the subtitle clearly says that this is an orthodox approach. That means that this is a set of lectures on classical thermodynamics. In other words, it does not take into account the fact that matter has a molecular structure. The point is that the subject of thermodynamics thrived well before we had learned about a microscopic picture of the material world. It indeed made huge strides and made the Industrial Revolution and our subsequent way of life possible at a time when most physicists did not believe in the existence of atoms. So we will try to avoid any mention of this microscopic structure of matter as far as possible in these lectures. Frankly, as far as classical thermodynamics is concerned, it does not matter whether a system is made of atoms and molecules or whether we have fairies dancing and turning little wheels inside. The particular predictions that thermodynamics makes will not depend on these details. The major reason why I am talking about classical thermodynamics is not really the fact that I dislike the microscopic structure. After all, today we do know that matter has microscopic structure, and we know that in great detail. And it gives us a huge amount of understanding of the world around us. But talking about classical thermodynamics and shunning, till perhaps the very end, its connection with the microscopic picture will help us, at least hopefully, illustrate the underlying clear logical structure of the theory. Classical thermodynamics happens to be one of the most logically concise and well brought together subject that we have in the realm of physics, and I hope that this set of lectures will make it possible for the viewer to appreciate the clarity of thought and logical prowess that classical thermodynamics brings to the table. Having said that, let me turn around and begin with a very brief foray into the microscopic picture of matter. For example, let us take a simple glass of water. Now, this glass of water typically contains around 200 milliliters of water, but for the sake of simplicity, I am going to consider that it actually has 180 milliliters. Now, it's easy to see why I chose this particular number. The molecular weight of water happens to be 18, so 180 milliliters of water, which is also 180 grams, is actually 10 moles. So that is roughly the amount of water in a glass. Now 10 moles would be 10 times 6 into 10 to the 23 molecules, or roughly at least of the order of 10 to the 25 molecules. And since describing the state of each molecule precisely means that we have to specify exactly where it is, that means 3 position components, as well as how it is moving, 3 velocity components, 6 in all. If we even don't worry about the fact that the molecule may be rotating and vibrating and stuff like that, even then, it turns out that we will need of the order of 10 to the 26 different parameters to describe something as simple or as small as a glass of water. However, you all know that to specify the state of the glass of water or state of water in a glass, we don't really need to bother about that many parameters. If we had to do that, we would never be able to talk about a glass of water at all. It will take us ages and ages and ages to list even a fraction of this many parameters. In contrast, what we really need are a very small number of macroscopic parameters. parameters which you can observe at the macroscopic scale, parameters like pressure, volume, temperature, etc. pertaining to this water. And once you specify these small number of parameters, you know perfectly well what the state of the water is. Now, why exactly is this possible? This is basically possible because the microscopic world in which the atoms and molecules reside is immensely tiny compared to our daily life world. In other words, in comparison with the microscopic domain, our macroscopic instruments that we use are A. too slow and B. too blunt. When I say too slow, what I mean is even an instrument that responds in, say, a microsecond, which is very fast for a large macroscopic instrument, is very slow compared to the scale of time at which atomic phenomena occur. The typical time scale of an atomic phenomenon is anything between 10 to the minus 12 to 10 to the minus 15 seconds. 10 to the minus 6 seconds, the typical response time of a rather fast macroscopic system, would simply be too huge compared to this atomic time scale. As far as too blunt is concerned, note that even if your instrument could resolve lengths of the order of a micrometer, that would still mean that in the distance it can resolve, there would be something around 10 to the 3, 10 to the 4 atomic separations. So the volume which you can see using this instrument would contain something like 10 to the 9 to 10 to the 12 atoms. A very huge number indeed. So what our instruments show us are not really microscopic properties at all, but rather time averages of these microscopic properties over what is an immense duration compared to the time scale over which these phenomena occur, as well as a coarse-grained average over a huge number of atoms. And ultimately, most of these microscopic parameters that we would be very worried about actually vanish under this kind of dual averaging. And only a very small number of combinations of these parameters ultimately survive to become observable in the macroscopic world. Now, which parameters exactly survive and why do they survive, which ones don't, that is a fascinating topic. And if near the end of this series, we find time to talk about the connection of this with the microscopic world, we will try to explain in some more detail why certain combinations are actually observable despite this immense bluntness and immense slowness of our instruments. But what is going to be very important in the coming lectures is that these parameters which survive and which we can observe in the macroscopic world using our slow and blunt instruments, these are what we call thermodynamic parameters. And specifying these parameters tells us all we want to know about the macroscopically observable state of the system. Now, the kind of thermodynamics we are talking about here is also called equilibrium thermodynamics. So in a sense, the name thermodynamics itself is a bit of a misnomer. You are really not talking about things which are dynamically changing. You are really talking about states which are actually not changing. That's what equilibrium really means. We are going to make this more precise in a moment. But note that even when we consider processes in which the state of a system changes, the most common thing that we are going to talk about are so-called quasi-static processes. Processes which happen so slowly. Indeed, even the adjective glacial would be really not appropriate for the slowness that we are trying to talk about here. Infinitely slowly or infinitesimally slowly, I don't really know what should be the right adjective here, may be the right way to describe this. These processes are such that at any given state the system, though not exactly in equilibrium, is very, very, very close to equilibrium. Infinitesimally close to equilibrium, if we want to be very precise. Now, since the development of classical thermodynamics, great strides have been made, especially in recent years, on the subject of non-equilibrium thermodynamics. But that is still nowhere near as strong a logical footing as the subject of equilibrium thermodynamics. We are going to confine ourselves to that in this set of lectures. So the first thing we need to do is to define exactly what equilibrium means. Now, the notion of equilibrium should be a familiar one, both from general day-to-day language as well as from other branches of physics. We usually tend to say equilibrium is a situation which a body is in when things don't change with time. In thermodynamics, the things that we are really talking about are the thermodynamic parameters. Those averages of microscopic quantities which ultimately are the only ones which are necessary to describe a state of a system. So we say a system is in equilibrium if its thermodynamic parameters do not change with time. Now, since physics is an empirical science and not an absolute dogma, this statement actually depends on measurements. What it really means is that the parameters, if they change too little to make a measurable difference over any reasonable time scale. That's what we really mean when we say that the system is time independent. Now, in addition to this one requirement, which seems very reasonable and meaningful, we have to add one additional restriction, which is the following. The state of the system is independent of its history. That is, the condition that the system is in will not depend on the path by which the thermodynamic parameters have obtained their present value. Now, the reason why we need to bring this in as an additional restriction is because we do have examples of systems where things may look like they're not changing with time, but the system has not really reached its true equilibrium state. A common example of that involves the annealing process by which iron is tempered to make it strong. If you take a piece of iron, heat it up, and then hit it with a hammer, and then cool it down, and repeat the process over and over again, at the end of a lot of such cycles, the final finished iron product will be a lot stronger than what you started out with. This actually shows that the thermodynamic properties of this system, in this case a block of iron, actually depends not only on what the current values for the thermodynamic parameters like pressure, volume, etc. are, it actually depends on what exactly was done prior to achieving these values. And if you tried to do full-fledged thermodynamics on a block of iron before the annealing process was completed, you would actually get erroneous results. Annealing the iron takes it closer and closer to the final equilibrium state. Well, one way to understand this, again borrowing a microscopic picture which we are really not going to talk too much about, is that there are many potential semi-equilibrium states which a block of iron can be in, where something called the free energy, which we will talk about a lot later on, but right now just think of it as something akin to energy, is close to a minimum, or rather is close to a local minimum, but not really a global minimum. It is the global minimum which would have given you an equilibrium state. Well, what this process of annealing actually allows it to is that it allows the system to get out of the trap of local minima when you heat it up and hit it. And finally, if you repeat it often enough, it will perhaps settle down in the true global minimum, from which it would be very difficult to dislodge it any further. So, when you keep on repeating the process and the properties of the iron that you get do not change over 2 or 3 such cycles, we say that the process has completed and you have a fully annealed piece of iron, one which is in its true equilibrium state. But for most of the time, we will essentially worry about the first part of the definition. That is, thermodynamic quantities do not exhibit a measurable change over a reasonable time span. Now, the subject that we are dealing with here, classical thermodynamics, can also be called equilibrium thermodynamics. It's really a study of the properties of systems in equilibrium. So, in order to proceed any further, we have to understand the notion of equilibrium, especially as used in thermodynamics, pretty clearly. And one of the first things that we need to do here is to talk about the different kinds of equilibrium that thermodynamics deals with. Now, while equilibrium is essentially the property of a single system, in thermodynamics we very often talk about what happens when we bring two systems in contact and talk about their joint or mutual equilibrium. And in this process, what is very important is a kind of walls that separate the two systems. Now, walls can come in many different forms. Some of the most important distinctions that we can make are: 1. The distinction between a rigid wall and a mobile or movable wall. The distinction between an impermeable wall and a permeable wall is a second. And thirdly, and this is going to be a slightly new kind of thing in thermodynamics, the distinction between an adiabatic and a diathermal wall. Now, the notion of a rigid wall as opposed to a movable wall is something that we can understand pretty easily from daily experience as well as from the notions of mechanics. If two gases are separated by a wall and the wall is rigid, cannot move, then each may be in equilibrium on their own despite having very different pressures. However, if you now replace the wall with a movable wall, these two systems will no longer be in equilibrium and the wall in between will move. However, if you wait a while, the system will reach a new equilibrium position, typically different from where you started out from. So, if these two systems, when they were separated by a rigid wall, the two states on the two sides, despite having different pressures, did not really affect each other. However, changing the wall to a movable one has ensured that now you come to a new kind of equilibrium. If you were to now change the wall back to rigid and then back to movable again, nothing should change any further. Now, two systems that are in equilibrium despite being separated by a movable wall, that is, basically two systems which exert the same pressure on the wall, are said to be in mechanical equilibrium. Now, this is a notion which is very important in thermodynamics, but it's really a notion which has been borrowed from a prior subject, that of mechanics. And we know that such a situation will be possible, especially if you have two gases on the two sides of the wall, if the two gases exert equal pressure on the wall. Now, let's come to the notion of permeable or impermeable walls. Well, if a wall allows material to pass through, then we have a permeable wall. Either all material or some kinds of material, in which case we would call it a semi-permeable wall. Now, if we have two systems which are in equilibrium with each other, that is, neither of their parameters change with time, in spite of being separated by such a permeable wall, you say that they are in chemical equilibrium. The compositions of the two sides don't change with time, and the situation has been reached where none of the components of one system migrate to the other side of the wall and land up in the second system. We will now come to this third kind of wall, which is uniquely thermodynamic in character. The notion that we are talking about is that of diathermal versus adiabatic walls. What makes this classification of walls special is that the two previous kinds of specifications are things we had already met before we come to thermodynamics. They are basically examples of pre-thermodynamic notions from chemical compositions or mechanics. But what can we say about this classification between adiabatic walls and diathermal walls? Now, very often we see textbooks define adiabatic walls as that kind of wall through which heat can't flow. On the other hand, the same textbooks usually end up defining heat as a kind of energy that flows through diathermal, that is, non-adiabatic walls. Now, you must realize that this definition is a circular one. On the one hand, you are defining adiabatic walls via the notion of heat flow, and then you are defining heat itself as the kind of energy which can flow when a wall is not adiabatic. This, of course, is not a very nice scenario to be in. To be logically consistent, what we do need here is a definition of adiabatic walls that does not need a prior notion of heat. Let us now try to understand what such a definition could be. And we will try to understand this using an example which should be familiar to most of you. So this is where a cup of hot coffee comes in. If you keep a cup of hot coffee in a switched-on oven, it stays hot. But keep it on the tabletop, it becomes lukewarm. Put it in the fridge, then it becomes really, really cold. So the state of the cup of coffee changes drastically depending on the state of its surroundings. However, if you keep the same cup of coffee in a thermos, then as long as you're doing this for a reasonably short period of time, whether you put it in the oven or on a tabletop or in the fridge, it should really not make a difference. The coffee inside will stay hot for a long, long time, irrespective of the surroundings. Now, we tend to say that this happens because heat cannot flow in and out of a thermos. But note that we don't really need to talk about heat at this stage. All we are saying is that the state of the coffee inside a thermos can be maintained at the same value, irrespective of the surroundings. So, adiabatic walls are idealizations of this particular feature of a thermos. Or, a thermos is a decent approximation to an adiabatic wall. Truly adiabatic walls do not really exist in real life, but as a thermos shows, we can get pretty close to a truly adiabatic wall. To put it more formally, the walls enclosing a system can be of such a quality that the state of a system will not change if it is brought into contact in succession with any set of other systems which are already known to be in mechanical and chemical equilibrium with each other. That last restriction is important because, of course, you may have a wall which is adiabatic but movable, in which case different states at different pressures, if brought in contact with your system, will change the state of the system. We don't want that to happen. So we have carefully selected only systems which are known to be in mechanical and chemical equilibrium with each other. But when you bring them into contact with this system, if the system does not change at all, then you say the walls are adiabatic. Of course, if the walls had been adiabatic, immovable and impermeable at the same time, this last restriction would not have mattered. But then we would not have been able to clearly distinguish between what part of the change, if any, of the system is being created by mechanical reasons or composition issues, and which are being created by this purely thermodynamic notion of an adiabatic versus a diathermal wall. Now, two systems which are in equilibrium